Hi guys, I'm Fera from Guitars AI, and I welcome you to another tutorial on the series where I will be discussing some algorithms, and I will be implementing the algorithms in 4 different programming languages. This time I'm also starting a sub-series inside the series because I want to talk about some algorithms in the basics of signal processing. So this will be the first one. It's a very basic algorithm, so it can be a good starting point if you're going to start and give your first steps into algorithms and into signal processing. It's much more simple than the previous, the merge sort, the first one I did in the series. And I'll talk about the average of a signal, so the mean, the arithmetic mean of a signal. And as a bonus, this time I'm also implementing in R and in Octave. I will not do this in other tutorials, but I just wanted to show the power of this environment where we can run multiple programming languages in the same Jupyter notebook. And I also wanted to refresh my Matlab Octave skills and to learn R. So this is why I'm also including as a bonus these 2 languages. So let's get started. As usual, the first configuration to run the Jupyter environment here in Python. So I'm using the NumPy, so I use arrays this time. And I'm also plotting with Matplotlib and pyplot. I'm displaying a web page inside the Jupyter, so I'm using also some display. I included logging, but I'm not using logging this time. And this is the same old function to display a web page inside the Jupyter notebook. So to test our function that will calculate the average or the mean of a signal, I decided to use as a test array, as a test signal, the half-rectified sinusoid. So why I decided this? First, because we know that the half-rectified sinusoid has a mean, so an average, that is the peak voltage divided by pi. So here we have an example of a sine wave. I'm not using a sine wave because the average of a sine wave is 0, and it's not good to test our function with something that is equal to 0. So if we will imagine our sine wave to be a voltage, and this is the peak voltage, and this so this is our sine, we would pass through a half wave rectifier, and all the negative parts of the sine wave will be 0, and we will end up with something like this. So we have here that the average, the mean of the this half rectified sinusoid is the DC voltage, and the value is the peak voltage divided by pi. In our case, we're going to decide to define the amplitude from -1 to 1, so the peak voltage is going to be 1, and here we'll have 1 divided by pi. That will be approximately 0.316. So you can read about the sine wave and the full rectification, half rectification. It's an interesting topic, but I will not cover in detail. So first we need to create our test vector. So we'll create the half rectified sinusoid. How I'm going to do this? So in Python, I came from Matlab school. So my first steps into scientific programming was in Matlab, and there are many different convenient functions, and I got used to use a Linspace to generate arrays with we can pass the number of points we want and the where to start and where to end. So I'm given here, so I want to calculate the sine from minus pi to pi, and I'm going to use 201 points. So I'm defining a linear array from minus pi to pi, and I know for that if I take the sign from minus pi to pi, it will be from 0 to 0, reaching a maximum of 1 and a minimum of a minus 1. So it's easy to build the signal. After this, I'm just, because I don't want to make any change on the original signal, I'm calculating the sign of x with this numpy sign, and then I'm copying this array to another array that I'm calling half sign of x, and then I'm using this very convenient Python way of assigning values to some kind of threshold. So everything what is smaller than 0 will be set to 0. Here I'm just plotting, so this is the sine wave, and here is this half rectified sine wave. So everything what is smaller than 0 is being set to 0, and this is the input signal we are going to test. As I'm using NumPy arrays, and most of the programming languages, you will find some libraries that will already calculate the mean. But as an exercise, we're not going to use it. We're just using here so we know, and we can test against our own function. So the mean of the sign, so the average of a sign, when we add up everything and we divide by the number of elements, it's going to be 0. It's more or less trivial and obvious to observe. But in the case of the half rectified sinusoid, we have the value which should be pi, 1 divided by pi, and we reach this this value of 0.316. So let's check if it's really 1 divided by pi. I can rerun the cells. 1 divided by pi. Let's see what we get. So it's slightly different, the values. Also, it depends on how I am creating the number of elements inside the signal. So this is not this is a digital signal. We're not taking infinite numbers from minus pi to pi, and the average can be slightly different. We can, for example, try to change the number of points. So we have a change here on the mean of our sine wave. Let's try with more points, 1001 points now, and we start to get a value which is closer to 0.318. That is the 1 divided by pi. Just for testing purposes, I'll keep using the 201 elements, keep things small. So this was in Python. So because we are using the same signal, we are not using this definition of a voltage peak divided by pi. We want to have this number after we calculate the average of any of these half rectified sine wave using our own implementations. So we have now a signal in Python. Let's do the same thing in JavaScript. So I'm not I'm not an expert in JavaScript, and I'm not sure if they already have a Linspace function predefined like we have in Python. So I had to define my own JavaScript linear space. So I'm passing a starting point, an end point, and a number of points that I want to have into this linear space. So I'm defining this function, and now I'm defining my half rectified sinusoid. So I'm calling this linspace from minus pi to pi using 201 points. Then I'm mapping this variable using the sinusoidal function from the math in JavaScript. And then I'm also doing this to do the half rectification. JavaScript, I'm not sure how are the plotting libraries in JavaScript, especially to use inside this Jupyter Notebook environment. So I'm using the power of the script of scripts. Am I exchanging variables from different kernels? So I'm getting the half sign of x JavaScript from the JavaScript kernel, which was defined here, half sign of x JavaScript in the JavaScript kernel. And now I am using Python to plot. So I have now the plot from the, we can see is the same half rectified sinusoid. Now in Java, I'm also implementing this Linspace function. I'm not sure if Java has already some library with this implemented, but it's a good exercise to do it by yourself. So we take a starting point, an ending point, the number of elements, and we're returning a double. So it's it basically executes this formula here, and we end up with an array from start point to end point with a certain number of elements. And I'm also doing here, using this linspace from -pi to pi, 201 points. Then I'm defining this half sign. Unfortunately, this script of scripts is not officially supporting Java, and we cannot use this get from Java that we use to plot in Python. So Java and C++, there are no support to exchange variables between kernels, and just we have here the values from the half rectified sine wave. Finally, in C++, I'm including some mathematic library. I'm using a vector, also numeric for vectors, and I'm defining a Linspace function, which is the same principle. We have a start and end, number of elements. It calculates this function and it returns an array in case it will a vector. In C++, I want to demonstrate the mean using two different data structures. So we can use a vector of double, or we can use an array of double. So I'm also creating an auxiliary function that would return a vector of doubles, and it could return a full sine wave or a half rectified sinusoid. So it depends if we set the half Boolean variable to true or false, it would return the sine wave or the half rectified sine. And here, so I'm having the half rectified as a vector of doubles, and I'm just doing this part here to have it as an array of doubles, so we can see how these both data structures work and how can we create the functions to calculate average for them. We have already our input vector signals, so we will use this half rectified sine that we already know. We calculated using a NumPy array mean, inbuilt mean method to calculate the mean of this signal, and we know that it's approximately, by theory, peak voltage divided by pi. So what is the mean or the average? So this is the formula to compute the mean. So it's the sum of all elements divided by the number of elements. So here in Wikipedia, you can read about the arithmetic mean, and it will be the same formula. So we sum the elements of a signal or an array, and we divide by the total number of elements. And this is the algorithm that we're going to implement: the sum of elements divided by the number of elements. So in Python, I'm defining signal mean. It takes an array, and we start with the mean is equal to 0. We iterate in each element of this array. So the complexity of this algorithm will be of O(n). We need to go through all the elements of this list once and sum them. So this is what we're doing here. In the end, we divide the sum of the elements by the size of the array, and this is the function. So we can print here, so I'm calling the signal mean of the sign of x, and we have here average as expected 0, and if we use the half rectified sign, we have the same value, very close to what the inbuilt NumPy array mean calculated. So this was in Python how we defined our signal mean function. Let's move on to JavaScript. Very similar. Takes an array. We define a starting sum of 0. We iterate over the elements of the array. The sum is the previous sum plus the current element. So we iterate and we sum, and then we return the total sum divided by the number of elements in the array. We can also test with the half rectified sign, and we achieve the same result. So here I'm also using this as kind of cheating, but there is this function. We can use the reduce in this array that will already gives us, it will iterate and it will gives us the sum of the elements of this array, and then we're returning the sum of the elements divided by the length of the array. We can also test for this, and we achieve exactly the same value. In Java, again, we iterate over the elements of an array of doubles, and we start with the sum equals to 0. On each iteration, the sum is equal to the previous sum plus the actual element, and we return the sum of all elements divided by the length of the array. We also test, and we have the same result. In C++, so now I am testing first using an array of double. So in C++, there is this thing that I'm passing a pointer to the first element of this array. And when we use this approach, it's not possible to determine the size of the array, the total size of the array, by the pointer to the first element of the array. So it's very common in C++ to see that we also need to pass the length of our signal as an argument to calculate our mean of the signal. But it's the same approach. We iterate over the elements, in this case for the total length of from 0 for element 0 until the end of the array. We sum, and then we return the sum divided by the length. So here we are testing using an array of doubles. So what I'm doing here is just I'm getting the length of the array by dividing the size of the array divided by the size of the first element. So using the size of, so I get the number of elements, and then I'm passing through as so we're passing a pointer to the first element of the array, and we also give the length of the array. But we can also use vectors, and so if we create a function, we define a function that will take a reference to a vector. This time the vector data structure, it has an inbuilt function that it returns the size, the number of elements. So there is also, using this metric library that included on the top here in this numeric library, we can call this accumulate, which is it will return us the sum from begin to the end of our passed factor, and we're returning the sum divided by the number of elements. We also test, and we have here the result, which is very similar to all previous results. So this algorithm is quite simple to implement, even when we are not using inbuilt functions to calculate the sum of elements of arrays or vectors. So we basically we're iterating over from the beginning to the end of an array or a vector, and we're summing all the values, and then we return the sum, total sum divided by the number of elements, as the formula describes this algorithm. As a bonus, there's a long time I don't do anything with Matlab Octave, so I decided to implement also in Octave. So it's the same principle, but there is already a Linspace function inbuilt in Octave. So I'm creating this linear space from -pi to pi. Then I'm taking the half of the sign, which is plotted here. Then I'm defining this function to calculate the mean, which iterate over the signal, the elements of the signal. It has the total sum here, and we divide the sum by the number of elements, and this is we're testing here, and we achieve this result. Finally, I almost never used R, so I decided to learn for this project, and here's also an implementation in R. I'm defining our input signal with the half rectified sinusoid. I'm plotting here from -pi to pi, and here's the rectified, half rectified signal. Then I'm defining a function to calculate the mean, so we iterate over the elements, and we're adding them together, having a total sum, and returning the sum divided by the length. So here also is the test, and we can see we achieve the same results. Sometimes we achieve different results because we are using different types of numbers. So it could be a float or a double. It depends what is being used internally when we don't predefine. So in languages like Java and C++, we already give it. We assign types to our variables. In some other languages like Python, it's done automatically unless you specify it by yourself. So this was the formula of the algorithm we wanted to implement. We sum the elements of a vector or an array, and we divide it by the total number of elements of this array. So this was a gentle introduction to algorithms. In signal processing, sometimes it's very convenient to calculate the average of a signal. So we can use, in most cases, you're going to be using inbuilt functions from libraries. Most of the times they are using the full power of a language with optimizations, and we don't need to do everything by ourselves. But it's a good exercise to learn how to implement some simple algorithms like this one. Here are six different programming languages, and that's it. That's Feta from Guitars AI, and I see you in the next tutorial. Check you later.